In the heart of a raging sea, even the wildest storm has its calm center's eddies, where the water spins in perfect balance, untouched by the chaos around them. So too in the cosmos. For all its turbulence, the three-body problem is not a wasteland of pure disorder. Scattered throughout its mathematical landscape are islands of stability, rare, delicate, and astonishingly precise configurations where three bodies move, not in panic, but in silent, synchronized grace. These are not approximations, not lucky accidents. They are exact solutions, mathematical miracles carved into the fabric of gravity itself. The first of these oases was discovered not by a stargazer, but by a dreamer of celestial mechanics. In the 1770s, the Italian-French mathematician Joseph-Louis Lagrange asked a deceptively simple question. Could three bodies orbit in such a way that their relative positions never change? He wasn't imagining them stationary that would collapse under gravity. But what if they rotated together as a single rigid structure, like beads on a spinning hoop? Lagrange found 5 such points, now called Lagrange points, where a small object, like a moon or a spacecraft, can sit in perfect balance between two larger bodies, such as the Earth and the Sun. At these points, the gravitational pulls and the centrifugal force from orbital motion cancel out exactly. 3 of them, L1, L2, and L3, lie along the line connecting the two big bodies. They are unstable, like balancing a pencil on its tip. A tiny nudge, and you fall away. But L4 and L5 sit 60 degrees ahead and behind the smaller body in its orbit, forming equilateral triangles with the two masses. These are stable if the mass ratio is right, and nature uses them. In our solar system, Jupiter's L4 and L5 points are home to thousands of asteroids called Trojans that have ridden along with the giant planet for billions of years, locked in gravitational harmony. Earth has its own Trojan asteroid, discovered in 2010. Even moons have them, Saturn's moons, Tethys and Dione. Each shepherd smaller companions at their L4 and L5 points. These are not just curiosities, they are cosmic parking spots. The James Webb Space Telescope orbits near Earth's L2 point, shielded from the sun's glare, cooled by the void, perfectly poised to peer into the dawn of time. Future lunar bases may use Earth, Moon L points as staging areas. Lagrange's discovery proved that even in the three-body problem, equilibrium is possible, but only under strict conditions, and only for systems where one body is negligible in mass. What if all three bodies are significant? Can they still dance together without tearing each other apart? For centuries, the answer seemed to be no. Then, in 1993, a breakthrough. Mathematicians Alan Chancina and Richard Montgomery, working independently at first, then together, discovered a stunning solution. 3 equal mass bodies could chase each other around a single, figure-8-shaped path, each following the same loop, perfectly spaced in time. No collisions, no ejections, just an endless looping waltz through space. It was so elegant, so unexpected, that many thought it must be a fluke. But simulations confirmed it. The figure-8 orbit is stable against small disturbances. It's not just math, it's physics. Since then, dozens of other choreographies have been found. Families of orbits where 3 or more bodies trace intricate, repeating patterns, triangles, lemniscates, braids in space-time. Some look like cosmic calligraphy. Others resemble the orbits of electrons in quantum models, though the physics is entirely classical. These solutions are vanishingly rare in the space of all possible motions. If you randomly place 3 stars in space with random speeds, the chance they'd fall into a choreography is effectively 0. But their existence proves a profound truth. Chaos does not mean lawlessness. Within the storm, the laws of physics still carve out paths of perfect order. And sometimes nature finds them. In 2012, astronomers discovered a real-world analog, a triple-star system called HD 188753, in the constellation Cygnus. 2 stars orbit each other every 150 days, while a third circles the pair every 3.5 years. Though not a perfect choreography, the system is stable. Its rhythms locked in a gravitational truce that has lasted millions of years. Even more astonishing is the system KIC 2856960, a triple star whose light curve, observed by the Kepler Space Telescope, pulses with such precise repeating complexity that it matches a theoretical 3-body orbit almost exactly. It's as if the stars themselves are performing a cosmic sonata written in gravity and light. But stability in the 3-body problem doesn't always require perfect symmetry. Sometimes it emerges from hierarchy. Imagine a close binary pair, a duo of stars whirling tightly around each other, and a third star orbiting far away, like a distant guardian. From the binary's perspective, the third star is just a faint, steady tug. From the third star's view, the binary looks like a single point of mass. In this configuration, called a hierarchical triple, the system can remain stable for billions of years. This is likely how Alpha Centauri works. Alpha Centauri A and B orbit each other every 80 years, while Proxima Centauri circles the pair at a distance of over 15,000 astronomical units. So far that it takes 550,000 years to complete one lap. Proxima's influence on the inner pair is tiny, and theirs on it is gentle. The system breathes slowly, calmly, like a sleeping giant. Planets can exist in such systems too. In fact, Proxima Centauri hosts at least 2 known planets, including one in the habitable zone. They orbit their small red sun, largely undisturbed by the distant binary, though over eons, subtle tugs may shape their climates in ways we're only beginning to understand. These hierarchical arrangements are the most common form of stability in triple systems. They're not perfect, but they're robust, like a family where 2 siblings are close and the third lives far away, visiting occasionally but never disrupting the household. Yet even these oases are not eternal. Over cosmic time, external forces intrude. A passing star might nudge the outer companion, tightening its orbit. Tidal interactions can drain energy. Gravitational waves, ripples in space-time predicted by Einstein, slowly sap orbital energy from close binaries, causing them to spiral inward. In dense star clusters, flybys are frequent, and even the most stable triple can be unraveled by a chance encounter. So these islands are not fortresses. They are temporary refuges, sanctuaries carved out of chaos by the precise tuning of mass, distance, and motion. And we have learned to navigate them. Space agencies use Lagrange points not just for telescopes, but as gravitational highways. By threading spacecraft through these delicate balances, we can travel vast distances with minimal fuel, riding the contours of space-time like sailors catching trade winds. This is the art of low-energy transfer, a direct application of 3-body dynamics. Even missions to the moon now use these principles. Instead of brute force trajectories, modern lunar probes follow chaotic but fuel-efficient paths that weave through Earth. Moon Lagrange points, arriving with grace rather than force. So the 3-body problem, once seen as an obstacle, has become a tool. It reminds us that stability is not the default state of the universe. It is a fragile achievement, a negotiation between forces, a moment of balance in an otherwise turbulent dance. And in that balance, we find not just survival, but opportunity. In the next chapter, we leave the realm of theory and simulation and turn our eyes to the real sky, to the actual triple star systems scattered across our galaxy, where the drama of the three-body problem plays out in fire, light, and dust. Look up on a clear night, and you'll see thousands of stars, each a distant sun, most appearing solitary, serene. But appearances deceive. Roughly half of all sun-like stars in our galaxy are not alone. They have companions. And among them, a surprising number live not in pairs, but in trios. 3 stars bound together by gravity, locked in a dance that can be harmonious, violent, or something in between. These are not hypothetical constructs. They are real, observable, and they are rewriting our understanding of how stars live, die, and shape the worlds that might orbit them. Take Alpha Centauri, the closest star system to Earth, just over 4 light-years away. To the naked eye, it appears as a single bright point in the southern sky, but through a telescope, it splits into 2, Alpha Centauri A, a yellow star slightly larger than our Sun, and Alpha Centauri B, an orange companion, smaller and cooler. They orbit each other every 80 years, their paths elliptical, sometimes as close as 11 astronomical units, just beyond Saturn's orbit, and at other times stretching to 35. But there's a third. Far out in the darkness, circling this golden pair, is Proxima Centauri, a faint red dwarf barely visible even in large telescopes. It takes more than 500,000 years to complete one orbit, tracing a path so vast it stretches over a light-year across. For decades, astronomers debated whether Proxima was truly bound to the central duo or just passing by. But precise measurements from the European Space Agency's Gaia mission confirmed it. Proxima is part of the family. This is a hierarchical AAA stable configuration where the inner binary and the distant third star barely disturb each other. And in that stability, something remarkable has emerged: planets. In 2016, astronomers announced the discovery of Proxima Ba, rocky world orbiting Proxima Centauri every 11 days, nestled right in the habitable zone where liquid water could exist. Later, a second candidate, Proxima C, was found farther out. These planets likely formed in the quiet gravitational shadow of their distant binary cousins, shielded from the worst of the three-body chaos. But not all triple systems are so gentle. Consider Castor, the second brightest star in the constellation Gemini. To ancient stargazers, it was one star. Then, in the 1700s, it was revealed as a binary. Later, each of those turned out to be binaries themselves. And then, a 6th star was found orbiting the whole ensemble. Castor is not a triple, it's a sextuple system, built from 3 binary pairs, nested like Russian dolls. Yet at its heart lies a tight triple subsystem, 2 stars orbiting each other every 9 days, with a third circling them every 300 years. Here, the gravitational tides are fierce. The close pair exchanges energy, spins, and even mass. The outer star tugs at their orbit, slowly warping it over centuries. It's a system in constant negotiation, stable for now, but with a future that could include stellar collisions, mass transfer, or ejections. Then there's the system that shattered expectations entirely, GW Orionis, located about 1,300 light-years away in the constellation Orion. GW Orionis is a young triple-star system, still surrounded by the dusty disk from which it formed. When astronomers pointed the Atacama Large Millimeter Array, the most powerful radio telescope on Earth, at it, they expected to see a flat, orderly disk like the one that birthed our solar system. Instead, they saw chaos made visible. The disk was torn in two. 3 separate rings, each tilted at a different angle, like misaligned records on a spindle. The innermost ring was wildly inclined, so much so that it appeared almost perpendicular to the others. And between them, vast gaps gaped open, as if something massive had carved them out. Computer models showed only one explanation: the gravitational pull of the 3 stars, orbiting in a complex, non-coplanar configuration, had twisted the disk apart. Their competing tugs didn't just perturb the dust, they ripped it into disconnected layers. And in the inner ring, astronomers suspect, planets may already be forming, born in a cradle of gravitational violence. This was the first direct evidence that 3-body dynamics can sculpt planet-forming environments in ways 2-body systems never could. Planets in such systems wouldn't orbit in a flat plane. They might circle at steep angles, or even flip their orbits entirely over time. Their skies would be lit by multiple suns rising and setting in unpredictable sequences. And then there are the systems that don't last at all. In dense star clusters, stellar cities, where thousands of stars crowd into a space no larger than our solar system, 3-body encounters are common. When a single star wanders too close to a binary, the resulting interaction is often catastrophic. Energy is exchanged violently. One star is flung away at high speed, becoming a hypervelocity star that escapes the galaxy entirely. The remaining 2 collapse into a tighter, faster orbit, sometimes so close they begin to merge. Astronomers have traced the paths of several such runaway stars back to the galactic center, where a supermassive black hole lurks. But others originate in clusters like the Orion Nebula, where triple encounters are frequent. These aren't rare anomalies. They're a fundamental part of how stars evolve in crowded neighborhoods. Even black holes play this game. In 2020, the LIGO and Virgo gravitational wave observatories detected ripples in space-time from a black hole. Merger unlike any before, one black hole was 30 times the mass of the Sun, the other 60. But the signal carried a twist. The black hole's spins were misaligned, suggesting they didn't form together from a single star. Instead, they likely met in a chaotic 3-body encounter in a dense stellar environment, where a third black hole, or star, slingshotted them together just before they collided. This means that some of the most energetic events in the universe, black hole, mergers that outshine entire galaxies in gravitational waves, are choreographed by the 3-body problem. And it's not just stars. Planets themselves can be players. In 2012, astronomers discovered a planet orbiting a binary star, Kepler 16b, the real-life Tatooine from Star Wars. Since then, dozens of such circumbinary planets have been found. But what about planets in true triple systems? In 2020, the TESS Space Telescope spotted a planet, LTT 1445a, be orbiting one star in a triple system of red dwarfs. The other 2 stars orbit each other farther out, creating a complex gravitational landscape. The planet's year lasts just 5 days, but its climate may be shaped by the varying light and tides from its 2 distant suns. Even more exotic is the possibility of a planet orbiting all 3 stars at once, a circumtriple planet. None have been confirmed yet, but simulations show they could exist in wide, stable orbits around hierarchical triples. If found, such a world would witness 3 suns rising and setting in a sky of ever-changing geometry. These real systems force us to confront a truth. The universe doesn't care about our desire for simplicity. It builds with whatever materials are at hand. 2 stars, 3, 6, and lets gravity sort it out. Sometimes the result is serene. Often it is turbulent, but always it is dynamic. And in that dynamism, new possibilities emerge. Planets in triple systems may experience extreme seasons, not from axial tilt, but from shifting stellar distances. A close approach of one star could melt ice caps. A retreat could plunge the world into decades of winter. Life, if it arose, would need to adapt to rhythms far more complex than Earth's gentle yearly cycle. Yet, paradoxically, the very chaos that threatens stability might also enable it. In some simulations, the gravitational kicks from a third star can nudge a planet into a more circular, life-friendly orbit, or prevent it from falling too close to its host star. Chaos, in the right measure, can be creative. We are only beginning to map this territory. With telescopes like James Webb, Gaia, and the upcoming Vera Rubin Observatory, we're discovering triple systems in unprecedented numbers, measuring their masses, orbits, and planetary companions with stunning precision. Each one is a natural laboratory. A real-world test of the equations Poincaré wrestled with, of the choreography his mathematicians dreamed up, of the limits of predictability itself. And in every observation, we see the same lesson. The three-body problem is not an abstract puzzle. It is written in starlight. It shapes solar systems. It flings stars across the galaxy. It may even decide where life can take root. In the next chapter, we ask the ultimate question: could a world caught in such a gravitational storm ever be home to life? Or is the three-body problem a cosmic barrier to biology itself? Imagine standing on the surface of a planet orbiting not one sun, but 3. Dawn doesn't arrive with a single golden arc. Instead, light crests over the horizon in waves. First a pale red glow from a distant dwarf star, then a sharper yellow blaze as the second sun rises, followed hours later by a fierce white glare as the third emerges. Some days, all 3 share the sky. Other days, only one shines. And sometimes, during rare alignments, they eclipse one another in a celestial ballet that plunges the world into eerie, shifting twilight. This is not fantasy. It is a plausible reality in a triple-star system. And the question is not just whether such a planet could exist, but whether life could survive there. At first glance, the odds seem grim. The three-body problem is synonymous with instability. Orbits can stretch, flip, or collapse without warning. A planet that starts in the habitable zone, the narrow band where liquid water can exist, might, over time, be flung into the frozen outer dark or scorched by a sudden plunge toward a star. Climate would be a gamble, not a cycle. Seasons wouldn't repeat. There would be no agricultural calendar, no predictable winters or summers, only a cosmic lottery where each year rolls the dice anew. But nature is more inventive than our fears. Life on Earth has endured asteroid impacts, ice ages, supervolcanoes, and shifts in Earth's own orbit that altered climate over tens of thousands of years. If life can persist through such upheavals, could it also adapt to the rhythmic chaos of a triple-star sky? The answer depends on one crucial factor: timescale. If gravitational chaos unfolds over millions of years, far longer than the lifespan of any organism, then life might never notice. Evolution works on geological time, not human time. A planet that remains in the habitable zone for 500 million years has ample opportunity for life to arise, even if its orbit wobbles slightly. But if chaos strikes on the scale of centuries or decades, then complex life, especially intelligent life that builds civilizations, may never get a foothold. So, where do real triple systems fall on this spectrum? In hierarchical triples, like Alpha Centauri, the inner planet orbits one star while the other two remain distant. The gravitational influence of the faraway pair is weak and slow-changing. Proxima b, for example, likely experiences only minor orbital perturbations over millions of years. Its main challenge isn't gravity, it's stellar activity. Proxima Centauri is a flare star, prone to violent outbursts that could strip atmospheres. But that's a separate issue from the three-body problem. The real danger lies in non-hierarchical systems, where all three stars are close and comparable in mass. In these, chaos can erupt quickly. Simulations show that planets in such systems often get ejected within 10,000 to a million years. Far too short for life to evolve beyond microbes, if at all. But there's a middle ground, systems that are temporarily stable. Some triple configurations enter long phases of quasi-stability periods where the orbits appear regular, even if they're destined to unravel eventually. During these windows, which can last hundreds of millions of years, a planet might enjoy a calm enough climate for life to emerge. Think of it like living on the slopes of a volcano that erupts every 500,000 years. Dangerous? Yes. Impossible? No. Even more intriguing is the possibility that three-body dynamics could enhance habitability in subtle ways. Consider tidal heating. On Jupiter's moon, Io, gravitational tugs from Jupiter and its neighboring moons flex the moon's interior, generating enough heat to power hundreds of volcanoes. In a triple-star system, a planet caught in a resonant gravitational squeeze could experience similar internal heating, keeping subsurface oceans liquid even far from any star. Europa and Enceladus show us that life might not need sunlight at all, just liquid water and chemical energy. Or imagine a planet whose axial tilt is stabilized not by a large moon, as Earth's is, but by the gentle, rhythmic pull of a distant third star. Such a configuration could prevent wild climate swings, creating a more stable environment than a single star system might offer. Then there's the light itself. Multiple stars mean multiple spectra. A red dwarf provides infrared warmth. A sun-like star offers visible light for photosynthesis. A hot blue star emits ultraviolet that could drive complex chemistry. A planet bathed in this blended starlight might host forms of photosynthesis we've never imagined, using pigments tuned to multiple wavelengths, perhaps even shifting their color with the seasons as different stars dominate the sky. Of course, too much UV could be lethal. But life finds shields, thick atmospheres, ocean depths, or biological sunscreens. On Earth, some microbes produce melanin-like compounds to survive intense radiation. In a triple-star world, such adaptations might be the norm. But perhaps the greatest challenge isn't physical, it's temporal. Civilizations need predictability to thrive. Calendars, agriculture, navigation all rely on repeating patterns. On a world where the length of the year changes noticeably over a human lifetime, or where the brightest star in the sky shifts every few generations, would science ever develop? Would astronomy be seen as a study of eternal laws or of capricious gods? This is more than speculation. It's a window into how environment shapes thought. In our own history, the regularity of the heavens inspired the first scientists. The Babylonians tracked Venus not out of curiosity alone, but because its cycles matched planting seasons. If the sky had been chaotic, would we have invented physics or mythology? Yet even in chaos, patterns emerge. Humans are pattern-seeking creatures. We find constellations in random stars, faces in clouds, rhythm in noise. On a three-sun world, observers might eventually discern the underlying mathematical order beneath the apparent randomness, just as Poincaré did. They might learn to predict ejections or close approaches, not with eternal formulas, but with probabilistic forecasts like modern weather models. Their science would be humbler, less certain, but perhaps more honest. And that humility might be a strength. Because the three-body problem teaches a profound truth, stability is not guaranteed. It must be earned, maintained, and sometimes surrendered. A civilization that grows up under such skies might develop a deeper respect for limits, for the fragility of order, the value of resilience, the wisdom of preparing for the unexpected. In that sense, a chaotic sky might not hinder intelligence. It might refine it. Still, the numbers are sobering. Surveys suggest that only about 10% of triple-star systems are stable enough to host planets in the habitable zone for more than 1 billion years, the rough timescale for complex life to evolve on Earth. And of those, many face other hazards, stellar flares, radiation, or lack of heavy elements. But the galaxy is vast. With over 200 billion stars in the Milky Way, even a 10% chance means tens of millions of potential cradles for life in triple systems. And we haven't even considered rogue planets, worlds ejected from their birth systems drifting through interstellar space, warmed only by geothermal heat or the faint glow of distant stars. Some of these may have originated in triple systems, cast out during chaotic youth, yet still carrying oceans beneath icy shells. Life, it seems, is stubborn. It clings to cracks in volcanic rock, thrives in acid pools, survives in the vacuum of space for short periods. If it can do that, perhaps it can also endure the gravitational tides of three suns. The cosmic lottery is not fair, but it is generous. And in its most turbulent corners, it may still deal a winning hand. In the next chapter, we turn from stars and planets to the machines we've built to understand them. Supercomputers that simulate the three-body problem, not with pen and paper, but with raw computational power racing against chaos itself.